Should I
Okay,
start?
it seems to be working. So, okay, not much to say other than I think next week we'll skip the seminar because of the Bootstrap school. There will be a intense schedule, and so we're very glad to have Yin-Chen from Perimeter. He'll tell us about ON, non-Wilson Fisher kinks, the confined phase transition, and beyond. Thank you very much.
Okay, yeah. So first of all, I hope to thank for this opportunity for me to share some of our recent work. As you may have noticed, I'm a condensed matter physicist. So it was really great fun for me to learn and start to work on conformal Bootstrap. And this cannot be done without those two really wonderful gentlemen who patiently taught me a lot about Bootstrap. And I feel that our interactions are really interesting, that since we have different background and we can share different perspective on CFTs. And I hope that the two communities can really interact more frequently in the future. Okay, so if you are interested in some of the details of our work, you can find this archive paper, which was recently posted. Okay, so I guess everyone here knows that if you bootstrap this single correlator of ON vector, you will find the Wilson-Fisher sitting at the kink of the bootstrap bound. And also many of you know that if you move away from this Wilson-Fisher kinks, you will find another family of kinks, which we will call non-Wilson-Fisher kinks. I think in literature, this family of kink was first reported in Otsuki's PhD thesis, where he focused on this family of kinks in 2D. And later, by Jujin Lee, he discussed this kinks in 3D and 4D. I think at this moment, it's still unclear about the nature of this new family of kinks. So then we just simply call it non-Wilson-Fisher kinks. And in this talk, I will tell you some special cases of this family of kinks in which we have pretty thorough understanding. Hope with those can inspire the event to eventually understand this family of kinks. Okay, so this is the outline of this talk. I will try to motivate you a little bit about non-Wilson-Fisher CFT, or more generally speaking, non-symmetry breaking CFTs in condensed matter. I hope that you will find some flavor about CFTs in modern condensed matter. And then I will talk a specific non-Wilson-Fisher CFT, that is deconfined phase transitions, and discuss its connection to this non-Wilson-Fisher kinks. And in the last part, I will talk about, I will give some general discussions about this non-Wilson-Fisher kinks. And so please feel free to interrupt me. Okay, so I guess everyone knows that in condensed matter, CFT usually appears at phase transitions. And here is a famous phase diagram of helium-4 that we get two familiar CFTs. One is this O2 Wilson-Fisher. The other is this 3D Ising CFT sitting at the tricritical point. And it was really a great achievement of numerical bootstrap in the last 5 years that people managed to get the most precise critical exponents that beat all the methods that we use in condensed matter, including numerical, like Monte Carlo, as well as some experiments measurements. That's a story about traditional condensed matter physics. And nowadays, in modern condensed matter physics, people are more fascinated with the so-called physics beyond symmetry breaking paradigm. One of the frontier is to the so-called gapped topological phases. These phases in the infrared are described by the topological quantum field series. One of the most famous examples are this so-called fractional quantum Hall state. There are also some proposal about applying those topological phases into some fancy technology, quantum technology, like topological quantum computation. On the other hand, on the other frontier is the critical points, some exotic critical points, or sometimes even critical phases that is described by CFT, and more importantly, it's a non-symmetry breaking CFT, or in other words, it's a non-Wilson feature CFT. So in few slides later, I will come back to this figure. So, and this talk will, of course, focus on those critical points or critical phases that are described by those non-Wilson feature CFTs. Okay, I guess the first example of this non-Wilson feature CFT in condensed matter actually appears in this spin 1/2 quantum spin chain. It's a very simple model that you have a 1D chain. On each side, you get a spin 1/2, and they are interacting with its nearest neighbor through this Heisenberg interactions. So note that it's a 1D quantum system. So it's in the infrared, you should use 1 + 1D or 2D quantum field series to describe it. And this model can be exactly solved using the so-called beta ansatz. And its ground state was found to be this Fermilian SU2 level 1 West-Zumino-Witten model. And there's a fun fact about this. I actually learned yesterday that this solution was obtained in 1931, which actually was 10 years before Ansatz wrote down his famous exact solution of 2D Ising model. Okay, and that's not just a toy model that we play with. Indeed, there are some very concrete materials that can realize these models, and people did various experiments on such materials 2 decades ago, and here is a picture for this so-called neutron scattering that effectively measures the 2-point correlation functions in the momentum space. You can say that this experimental data agrees with the exact solution in a very reasonably. And in particular, you can say this light cone structure. You can also extract some critical exponents from those data. So that's really a nice story about CFT that is not like the minimal model type of CFT, appears in a very simple condensed matter system. And the physics becomes even more interesting if you go to 1 dimension or higher. That is, you consider a quantum spin 1/2 on a 2D lattice. Again, that will be like a quantum field theory in 2 + 1D or 3D. So, so there are 2 broad classes of lattices in 2D. That's a key difference from the 1D system. There you only have 1 type of geometry. The first broad class is called this bipartite lattice. And those include this Fermilian square lattice as well as the honeycomb lattice. The other more interesting and exotic type of lattice is called this frustrated lattice. It is built, its basic building block are some triangles as shown here. So you can get this so-called triangle lattice or the so-called Kagome lattice, a little bit more complicated looking. So a key ingredient here is the so-called frustration that you can easily appreciate by looking at single triangles. Imagine that on each side, you get spins interacting with its neighbor into some antiferromagnetic interactions. So then each spin would prefer to antiparallel with its neighbors, but since we have a triangle, it can never be done perfectly for all the spins. This is called the frustration problem. And at the end of the day, you will, if you just have a classical system, you will end up with extensive ground state degenerate manifold. And then quantum fluctuation will cause some coherence between those extensive states, leading to some very exotic phenomenon. That's it. Indeed, is a very big industry in condensed matter to consider this frustrated system. And so on top of this frustrated system, you can consider a simple generalization of this 1D Heisenberg chain. That is, you consider 2D lattice, this so-called this Kagome lattice, look like this. Again, you just put spin 1/2 on each side, and you have those spins interact with its nearest neighbors with antiferromagnetic Heisenberg interactions. It's a very simple model. However, it's super challenging to solve it. Indeed, it's a long-standing puzzle about its ground state for 3 or 4 decades. And to many people, this problem is actually the holy grail of the quantum magnetism. And I think so far, there's no consensus that the community has not reached the consensus that what is the ground state of this quantum Heisenberg model. But it's started to converge to an answer that similar to this spin 1/2 Heisenberg chain, the ground state of this simple model is again a conformal field series in 3D. And more specifically, it's a QED3 theory with 4 flavored Dirac fermions interacting with a dynamical gauge field. So people call it Dirac spin liquid. And it's not just a toy model for we theorists to play with. Indeed, there are several materials to realize it. One of the most famous one is this so-called Herbert-Smithite with its chemical formula like this. You don't really need to read it. I just want to show it to indicate it's a real business. And here is a picture for this compound. And as you can see that it's actually a 3D compound, but it's a layered compound. Like in each layer, you get this 2D Kagome plane with spin 1/2 sitting on it. And the interaction between the different layers are so weak that you can just simply ignore it. So, and this, what's really nice for this CFT is that it's not a critical point. It's actually a critical phase, or in other words, it's a conformal phase, because it doesn't have any relevant singlet. In other words, in reality, you don't need to tune anything to hit this CFT. I can just hand you this rock, then you automatically have a CFT inside it. The only thing you probably need to do is that you want to keep the temperature to be not that high, such that you see the quantum effect out of this rock. But maybe that is not so hard to achieve. For example, you can just go to some cold place, like Canada I'm living in, then you automatically have a CFT living in this rock. So I feel that's really a cool stuff, and probably that's so far that's the coolest CFT that we can get out in the condensed matter system. Of course, there's some work that both theoretically and experimentally to be done to eventually find CFT in such a rock. In this talk, I don't have a chance to really say more about this. Instead, I will go to something this exciting, that is the so-called bipartite lattice. So again, we can just play the game that we put spin 1/2 on this square lattice, and we have them interact with this antiferromagnetic Heisenberg interactions. The ground state of this guy turns out to be a rather boring state. It is a magnetic order state that spontaneously break your spin rotation symmetry. And this state is called a null state. On the other hand, what you can consider is that we consider some more complicated Hamiltonian that involves interactions between 4 spins look like this. So it's typically like you have a pair of spin like this interact with a pair of spin like this. And the Hamiltonian itself doesn't break the lattice symmetry, meaning that you also have like this pair interact with this pair. So this state, it turns out that the ground state of this guy, this Hamiltonian is will spontaneously break the lattice symmetry, but preserve the spin rotation symmetry. this state will have like some pairs of spins forming a singlet like this. And this state is called the valence bound solid state. So now comes an interesting question that what if you connect those two Hamiltonian, and can you get a phase transition out of it? So at the face value, you might think that the phase transition between those states will be a first order, because those two states breaks different symmetries. So then you cannot write down Landau's symmetry breaking phase transitions or Wilson-Fisher phase transitions to describe them. But it turns out that there's a way out, and this phase transitions is called the so-called deconfined phase transitions. So this brings to the second part, that is the deconfined phase transitions, and how we kind of try to bootstrap this deconfined phase transitions. Okay. So any questions so far? Okay.
So I have a question. So may I ask some question? So you
Yeah.
just mentioned that we can realize the 4 flavor created 3 IR fixed points from the inner stone in rock.
Yeah.
So here the 4 flavor number, I guess you mean in terms of 2 component Dirac framing, right?
Yes. Okay.
So my question is that, do you know if there's some experimental observation about the critical indices of this safety?
It's rather difficult to do at this moment because one thing is that there are some impurities in the materials. They have some challenge to get it more clean. And also, I think that's the major obstacle. But maybe in few years, they can get some better data. Yeah.
Okay, thank you.
Yeah. Okay. So, okay, let's go to the second part, this deconfined quantum critical point. So as I said, you cannot use a Wilson-Fisher or symmetry breaking type of theory to describe the phase transitions between this null state and the valence bound solid. But it turns out that you can write down a gauge theory to describe these phase transitions. And this gauge theory is rather simple, that you have 2 complex scalar interacting with a U1 dynamical gauge field. Okay, and the null state can be simply understood as a phase that you have those complex boson condense. And by condensing the complex boson, you will break the flavor rotation symmetry of those 2 complex scalars. That turns out to be just the spin rotation symmetries, SO3 spin rotation symmetries. On the other hand, if those complex scalars are gapped, you will get a pure U1 gauge field in 2+1D. And we all know that it will confine through the so-called monopole proliferations. And moreover, the monopole will carry some lattice quantum number. So then its proliferation or its condensation will lead to a lattice symmetry breaking. And that this lattice symmetry breaking state turns out to be the valence bound solid with such pattern. Okay, so this is a gauge theory to describe these phase transitions. The next question we can ask is, what is its global symmetry? At the face value, you might think the global symmetry of this quantum field theory is just SU2 cross U1, as U2 comes from the flavor rotation. U1 is a topological symmetry of the U1 gauge field. However, a very remarkable results from this paper, they find that numerically, they find pretty strong evidence that this phase transitions has an emergent SO5 symmetry. And later, there was a pretty well or beautiful theoretical understanding that why you get emergent SO5 symmetries out of from this scalar QED theory. So it turns out that there are a web of theories are due to each other, and from which you can tell that this theory should have an emergent SO5 symmetry. So first of all, this scalar QED3 indeed are self-due to another scalar QED3 theory. They are Lagrangian, identical, but the symmetry implementations, like the SU2 and U1 implementations, are pretty different. And at the end of the day, just from this, you can get emergent SO5 symmetry. And it will. This theory is also due to another self-due theories, that is Fermanic QED3 Grossner-Wu theory. And all those theories are further due to QCD theories with flavor 2 fermions coupled with SU2 gauge field. And for this theory, then you get an explicit SO5 symmetry. And further conjecture is that this QCD3 theory will be due to a SO5 nonlinear sigma model with a level 1 Western weighting term. So this is really a very beautiful duality web for a simple gauge series. And and this theoretically suggests that you should expect an emergent SO5 symmetry out of this deconfined visualizations. And then this will bring a strong constraint on some scaling dimensions for this critical theory. And more specifically, if this deconfined phase transition has an emergent SO5 symmetry, then there's a prediction that is there will be no relevant SO5 singlet. The tuning parameter for this phase transition is actually SO5 rank 2 tensor, symmetric rank 2 tensor. So now, if you get a CFT without relevant SO5 singlet, then you can use numerical bootstrap to get some bound for the scaling dimensions. Here is a plot with the SO5 symmetry, and you can say that this axis is a scaling dimension of O5 or SO5 vector. This is the SO5 singlet. So now,
naive question on the previous slide.
Yeah.
This SO5, not the last theory on this page, is a 2D theory, but the rest are
3D. It's 3D theory. All the theory are 3D theory.
Okay. Usually the nonlinear sigma model is in 2D, but okay.
I guess you worried that the nonlinear sigma model is not renormalizable in 3D.
Okay, I just usually thought of the nonlinear sigma model as in 2D, but
yeah, you can write down a nonlinear sigma model
in
any dimensions. Yeah, the question is whether you can solve it or not.
Okay.
But what is the Wessumino term in 3 dimensions?
It's similar to the. I will come back to that in 2 slides. Okay, can I postpone it? Okay. So you will have the. So if there is no relevant singlet, then you will get a strong bound. That is, the CFT can only live on the right-hand side, not this side. And then that means the scaling dimension of the O5 vector or the eta should be larger than 0.55. However, numerically, what people find among various quantum Monte Carlo groups, people constantly find that the eta is around 0.2 and 0.3, so which is strongly inconsistent with this strict numerical bootstrap bound.
Can I also comment, since you've mentioned Sandvik, that Sandvik would actually claim that there isn't an SO5 symmetry? That is, he's not finding numerically that there's evidence for an SO5 symmetry. He took the system to larger volumes, and there he was able to show that SO5 is actually violated.
I'm not sure which work you were talking about. I know he has some recent work, but it's a different model. It's not the original model, and and I think this guy, Adena, can achieve the largest possible system size, much larger than Anders Sandvik, I think. So there they still say SO5 symmetry. What Anders say is could be some other universality. That's something I don't know. But yeah, but thanks for the comment. One way out is that maybe for the deconfined phase transitions, there is no emergent SO5 symmetry. That's one way out. And the other way out,
I also have a question about this plot. Sorry, because I don't understand how the numbers I see on the axis, how they match with this number 0775 that you have on the slide, because it looks like the transition to irrelevance happens.
Yeah,
at
sorry,
0.8.
Yeah, thanks for the comment. I think I grabbed those two from independent place. I didn't really check. Yeah, thanks for the comment. Yeah, I think in literature it was recorded like this, and probably that was some more accurate calculation. Yeah, I think it's pretty easy for numerical bootstrapper to reproduce these results. Yeah, but sorry, I think I made a mistake here. Yeah, thanks for the comment. Okay, so one way out is that is a conjecture that maybe the SO5 deconfined phase transition is slightly non-unitary. And this idea was firstly proposed in this paper. They mainly talk about duality that I showed before. And later, this idea was sharpened, and also a lot of concept was clarified in this very beautiful paper. They call this phenomenon as the complex CFT. In condensed matter community, we used to follow their terminology. We call this as pseudo-criticality. So I guess many of you might already be familiar with this concept of complex CFT. So I won't really explain it again. Instead, I will just spell out a concrete theory that describes the scenario for how this SO5 deconfined phase transition becomes complex or becomes pseudo-critical. So this theory was proposed by my colleague and also Chong Wang and also Adena Hu independently. So the idea is that now let's just consider a nonlinear sigma model, and it defined in a 2 plus epsilon dimensions with an SO4 plus epsilon symmetry. And when epsilon is 0, then this just recovers to the Fermilian SU2 level K Westermann-Witten model. Here, this N is an SO4 vector. It's slightly different from what people usually do, that they write some SU2 matrix in this nonlinear sigma model. Here, you just rewrite this SU2 matrix in terms of an SO4 vector. So for epsilon equals 0, you get this Fermilian
SO4 vector.
Yeah, SO4.
Is that a unit vector? Unit vector, or
yeah, it's a unit vector.
Or
yeah, it's a unit vector. Yeah, that's why it's nonlinear. Yeah, that's. Yeah. And so the Westermann-Witten term is really just like N1 partial 1, N2 partial 2, N3 partial 3, N4, things like this. And for epsilon equals to 1, K equals to 1, you get this one of the dual description of the SO5 deconfined phase transitions. As I said, the nonlinear sigma model is well defined in any dimensions. And to have the Westermann-Witten term to well defined, you have you should rely on this homotopy group that has Z classifications, and it's true for epsilon to be any integer. So of course, mathematically, it only makes sense if epsilon is an integer. However, so I'm a condensed matter physicist, so sometimes we are sloppy on things. So we think that it may be still plausible or to some extent, it makes sense if epsilon is some fractional number. We know what fractional dimension means. We kind of know what fractional symmetry means, thanks to Slava's paper. So maybe it still makes sense to think about this model in fractional dimensions. And then you can they use some large K expansions starting from the 2D Gaussian fixed point to obtain an RG phase diagram as shown here. So the horizontal axis is a coupling constant, that is this G, and the vertical axis is the epsilon that we will use for the dimensional continuation. Okay, so when epsilon is 0, we are sitting at a 2D, then we are quite familiar with what is happening. That is, this Gaussian fixed point is unstable, it's repulsive, and it will be attracted to this non-trivial SU2 level K West-Zumwalt model. So now, if you turn on a finite epsilon, the Gaussian fixed point will actually become attractive. By Gaussian fixed point here, I didn't mean this gapless or critical Gaussian fixed point. It's really a Gaussian fixed point with spontaneous symmetry breaking, or the uncondensed. So then it's an attractive fixed point. So on the other hand, the West-Zumwalt fixed point will still stay as an attractive fixed point as long as epsilon is not too large. So then just by looking at those two fixed points, you can easily convince yourself that you get a new fixed point, a repulsive fixed point, or in other words, a UV fixed point in between. So then you get some RG flow like this. As you further increase epsilon, just using the large K expansion, they find that those two fixed points will approach to each other. And then at some critical epsilon, those two fixed points will collide, will merge and further collide and disappears to the complex plane. And this is a phenomenon described in this paper and called complex CFT. In some literatures, it was also called conformality lost. Okay, so that means if epsilon is larger than this critical epsilon, then you will not really get a real fixed point in your real plane. Although you still get a fixed point in the complex plane, and if the epsilon is close to the critical epsilon, then the complex fixed point will be pretty close to the real plane. That means even though you don't hit this true fixed point, you will still say its shadow, then you will get some approximate conformality, or in other words, you get some pseudo-critical behavior. You can also call it as some walking behaviors in the RG flow when you flow nearby this complex fixed point. So and this will explain a lot of phenomena, including the pseudo-critical behaviors seen in the quantum Monte Carlo simulations. Okay, so this is the idea about how to think about this SO5 deconfined phase transitions in this pseudo-critical scenario, and they did large K expansions to say some features. And what I'm going to do next is that to try to bootstrap this, because as you know, in bootstrap setup, you can easily go with fractional dimensions and the fractional symmetry, and we can say what is happening there. Okay, so the first thing we need to do is that we need to say whether we can get SU2 level 1 West-Zumwalt model out of this conformal bootstrap. So as you know, the West-Zumwalt model has a SU2 left symmetry and SU2 right symmetry. By combining them, you can get an SO4 symmetry. So here is how to identify the wraps in terms of two SU2s with the wraps of the SO4. Okay, So, and what's important for us to proceed is to understand some operator contents of this Westermann-Witten model. The most important thing, one is those Kazhmoudi primaries, which we can label as this in terms of this as you choose wrap. So in the vector SO4 vector channel, the lowest lying operator will be the Kazhmoudi primary with this scaling dimension. In T channel, the lowest lying operator for k larger than 1 will again be a Kazhmoudi primary with this scaling dimension. And for any k, you can also write down another operators, which is a Virasoro primary, but not a Kazhmoudi primary. And you can just get it by applying the Kazhmoudi generators into the vacuum, and you get this operators with scaling dimension 2. Okay, so that is a basic operator content that we need to and then numerically what we do is just the standard one that we consider the 4-point correlation functions of an O4 vector. And numerically, as you may know, that we don't quite distinguish O4 from SO4. Okay, so and this is what we get just by considering the O4 symmetry in 2D. So the first thing you can say is that the SU2 level K Westermann-Witten models seems to saturate the numerical bound, and this black solid curve just corresponds to the SU2 level K model. There's some discrepancies for SU2 level 1, and I believe that's just due to the numerical convergence. And on the other hand, you will say a kink, and this kink precisely corresponds to SU2 level 1. And from this operator contents, you can easily understand that why you get a kink corresponding to SU2 level 1, because the leading operator in the T channels for k larger than 1 is this Kazhmoudi primary, but it becomes a null state, or in other words, it decouples from the system at SU2 level 1, leaving its leading operator to be operator with scaling dimension 2. So this is a very nice example that you say understand that why this CFT lives at a kink. So that's a story for the 2D, and we can now let's try to go one step further. Try to say what will happen if we try to connect 2D, try to continue from 2D to 3D. As I said, what we want to pretend is that this nonlinear signal model is still well defined for epsilon dimension. So then in 2D, we get this familiar SU2 level 1 Westermann-Witten model. In 3D, we get some SO5 nonlinear signal model with level K Westermann-Witten term. And indeed, you can derive, to some extent, you can show that this model is due to a family of QCD3 theories that with two flavors of Dirac fermions interacting with a USP2K gauge field. For K equals to 1, that's just this SO5 deconfined efficientizations. That one of, as I said, one of the dual descriptions is some SU2 QCD theories. That's just at USP2. So then it's pretty, so then let's try to say what is happening as we try to push it to 3D. So this is the results that we obtained in fractional dimension. So again, I want to reiterate that we consider an SO4 plus epsilon CFTs in 2 plus epsilon dimensions. And on the left-hand side, that is the numerical bound for the rank 2 symmetric tensor. On the right-hand side, that's a bound for the SON singlet. So here, the dark plot corresponds to a small epsilon, like epsilon equals to 0.2, 0.4, and so on. Here, a light plot actually corresponds to a small epsilon, and here is epsilon equal to 0.2, 0.4, and so on. So from both plots, you can say that the kink survives at small epsilon, but it becomes weaker and weaker as the epsilon increases. And around the epsilon equals to 0.7, the kink becomes super weak that it's hard to really see it just by staring at it. But if you look at it hard enough, you can still find some super weak kink. But I think when you go to even large epsilon, then there is no kink left at all. So this tells us that maybe what is happening here is that this CFT at small epsilon, this kink still corresponds to this nonlinear sigma model. But frankly, there's no priori that should always be the case. But if we assume this is true, then what we are seeing is that this kink becomes weaker, probably indicates that eventually it disappears because it gets colliding with another fixed point. So this is consistent with this fixed point collision scenario. In other words, this complex CFT scenario.
Sorry, but
so,
I have a question, sorry. In fractional dimension, you lose unitarity anyway.
Yeah.
So, sorry, there seems to be two distinct violations of unitarity that are going on here, but you're only getting...
Yeah, that's something I don't understand, but I guess everyone knows that the Wilson-Fisher also, you get kink of Wilson-Fisher and you get island of this Wilson-Fisher at fractional dimension. So yeah, I guess something similar is happening here. As in one of Slava's paper, they argue that maybe the non-unitary operators is so high that it's not detected in numerical bootstrap. That's one possible explanation, but frankly, I don't know. Yeah.
I think that there is some difference between and after annihilation of the fixed points, because before the annihilation, your coupling is real, and then after annihilation, it becomes imaginary. So you would expect, I guess, that generically most operators will become will get imaginary, like complex anomalous dimensions, whereas before, while the coupling is real, it's possible for only for some heavy operator.
That's a good point. Yeah, that's a good point. Yeah, thanks.
I also have a question.
Can I ask a question?
Yeah.
So when people find these islands in when the dimensions are not integer, as you say, you still find islands, but do we believe that the values are correct for those islands?
It's agrees with epsilon expansion. That's the only tool that you can study epsilon dimension.
I see. But it's convincing that if you do epsilon expansion, the islands are where they should be.
Right. It's consistent.
I see. Okay. Thank you.
Yeah. And I think it's unclear, if I'm wrong, correct me please. So I think it's unclear that whether at epsilon dimension, if you increase the lambda, then the kink might disappear. That's one possibility. Or the island might disappear. That's one possibility, but people have not really seen it yet.
Thank you.
Can I also ask a question, Yin-Chen? So
yeah.
So the one feature of the fixed point annihilation scenario is that when it happens, we should see that there is some singlet operator which crosses marginality, and it should approach it in a particular square root-like feature, which is very characteristic. Do you see any support for this in your plots?
Yeah. So that's a good point. So you can say that in this plot, actually we plot it as delta S minus D. So that's the reason why we plot it this way. So then what you can say is that this scaling dimension approach the space-time dimensions, right, as epsilon increases, but it's not quite there yet. So as you said, the theoretical prediction is that when you have fixed point annihilation, it should be precisely goes to 0. But here it's not. I think there are several reasons. One reason is that numerically, due to some mysterious reason, the convergence in the single channel is pretty poor. I don't think people really understand it why, but in the rank 2 symmetric channel, it converges much better. So that is one reason that it doesn't exactly hit 0 when the kink disappears. The other reason is that since the kink becomes super weak before it disappears, so then it's hard to locate the precise critical dimensions. It is possible that the critical dimension is 2.8, and then you will say that plot becomes even lower. And as you improve numerical convergence, then you probably will say it hit 0. That's just possibilities. I think it's reasonable, but there still needs some work to really confirm it. Yeah.
Can you do epsilon expansion?
They did. They did.
Oh, they did.
Yeah.
Okay.
Yeah. They did one loop calculations. Yeah. Basically, what they did is just using Witten's famous results and then plug epsilon into this. Yeah, that's also what I said, what I wrote here, that the one loop value is like 2.77, which also seems to agree.
I had a question about
and if you compute the marginal dimension, what is it? If you compute the epsilon expansion, if you compute the dimension value is supposed to become marginal.
At one loop value is 2.77. That's
no, not the space-time dimension. I mean the dimension of this delta S scalar.
That's exactly marginal, right? At the collision point. Yeah. You can see it from just the beta function.
Yeah. Can you previous slide?
Yeah.
Yeah. So you mentioned here the connection with this USB 2K gauge theory.
Yeah.
This I assume with 2 fermions, right? You're talking when you F equals 2, you mean fermions.
Yeah.
So the Witten term comes from integrating out the fermions. But this model is known to have first order transitions at large K.
Yeah, that's true.
That it's a first order in 3 dimensions.
Yeah. Yeah, that's true. Actually, that's the next slide about.
Okay.
Yeah, thanks for the comment. Yeah. So, okay. This is the results for this kink and fractional dimension, and you say it disappears, which is consistent with this complex CFT scenario. And I think they still have some work to do to really conclude it. So now that's just quickly try to compare it, these results with some well-known results, that is Z2 Bootstrap. So we know that in 2D that if you do this Z2 Bootstrap, you get icing sitting at the kink, or the minimal model saturating the numerical bounds on the right-hand side of the icing CFT. And this the SU2 Witten story that I described is nothing but a mirror version of this famous 2D results. You get SU2 level K sitting at the kink, and all the SU2 level K are saturating bound on the left-hand side of the kink. And for Z2, if you continue it to 3D, then you still get icing sitting at the kink, and probably this super icing numerically seems to saturate the bootstrap bound. And all other minimal models are very likely to die in 3D, as we know that straight-state pulse model is a first-order visualization in 3D. So I would bet that probably all the minimal models just all die out through this mechanism of this fixed point collision. Yeah, that's my guess. And I think so. In this case, only 2 CFT survives. And go back to this the story that we are focusing on. So as Zoha commented, for large K, you naturally expect that it will be first order. So, and for K equals 1, it seems again to be first order. So, and intuitively, you would say that for as k increases, then it becomes more and more strong first order. So then in this case, it's a little bit unfortunate that all these families, as you continue to 3D, all of them becomes complex. So although it's a little bit unfortunate story for us, but I think there's still some interesting structures, similarities between those two, and maybe we can, from which we can maybe learn something that is useful to understand the structures of other CFTs. Okay. So now let's move to the last session that I will talk about some general features of this non-Wilson Fisher kinks. Okay, so first I want to compare the Wilson Fisher kinks with the non-Wilson Fisher kinks just through some simple observations. This Wilson Fisher kinks, which is Wilson Fisher CFT, it only exists between 2 and 4 dimensions, and it exists for any n. In contrast, this non-Wilson Fisher kinks, indeed, it exists in any space-time dimensions, but it only exists if n is larger than some critical value. As I showed before, that this kink can disappear for small n. And the other observation is that the Wilson Fisher kinks are pretty close to the Gaussian. And in particular, if you consider n goes to infinite, the scaling dimension of the ON vector and the ON rank 2 tensor will just go to the Gaussian's value. In contrast, the non-Wilson Fisher kinks are actually pretty far away from a Gaussian. And as n goes to infinite, you will see those two scaling dimensions goes to d minus 1 to d. So this just at the face value, you can easily tell the difference between those two different families of kinks.
Sorry, excuse me, I have a question. You say that the Wilson Fisher kinks are only observed between 2 and 4 dimensions. I mean, you observe them above 4 dimensions. It's just believed that they correspond to theories that aren't entirely unitary. But like, if you're just talking about visually seeing a kink, you see them. And in particular, I would say that it's similar to what's on your right-hand side, where, for instance, in 5 dimensions, you see them for a certain value of n, and then you stop seeing them for a sufficiently small value of n. So I think the story is somewhat similar.
Okay, yeah, actually, I don't know that. So are they, so position-wise, they are pretty far from each other, is it true?
I mean, I don't know about the non-Wilson Fisher kinks. I'm just saying that like the kind of Wilson Fisher kinks you see below 4 dimensions, you see them above 4 dimensions. It's just believed that they no longer correspond to a unitary theory. So presumably at infinite precision, they would go away, but you certainly see them.
Okay, yeah, thanks for the comment. Yeah, actually, I don't know that. Yeah. Is it possible that the kinks say in a D larger than 4 is actually this family of kink?
Oh, I mean, I don't know. I mean, I believe they're thought to correspond to ON models above 4 dimensions, and it's just that they have very small complex corrections due to some large n instantons.
Okay, good. Yeah, thanks. Yeah. Okay. So, yeah. Okay, now in 2D, it turns out that the critical n is just a 2. That means if you consider O2 symmetry in 2D, you will not see a kink. However, you still see something interesting. That is, what you can find is that the numerical bounds for the rank 2 tensor is actually saturated by this Fermilian O2 free boson from all the, even goes to a very large delta phi. Again, there's some discrepancy just due to numerical convergence, I believe. So this tells us that, yeah, so this, those bounds and we also may correspond to something interesting. So this is 2D04. And the other thing that we observe numerically is that in 2D, it seems that on the left-hand side of the kink, the numerical bounds seems to follow a very simple relations as shown here. And it's true for, and it's also coincide with O2 free boson, this SU2 level k as well as n goes to infinity. So it will be interesting to know whether there's some like one can write down an exact 4-point cohesion functions that solve this bound. So how much time do I have?
Let's see. You have, in principle, 5 minutes. Do you need more?
Maybe 10.
Yeah, that's fine.
Okay, yeah, let me try. Maybe I can finish it in 5 minutes.
Don't rush.
Sorry to interrupt. I missed it. Did you know the conjecture interpretation or the real of these kinks in 2 dimensions for large N?
No. In infinite N we know. Yeah. But
Thanks.
for general N in 2D, we don't know what does it correspond to. Okay. So now comes to the last case that we managed to understand it exactly. That is in the infinite N limit. So as I mentioned, for any space-time dimension, this in the infinite N limit, this kink states as a pretty simple number. That is the scaling dimension of O(n) vector and the rank 2 tensor is d-1 and 2d. So here is just a plot for 3 dimensions. In any space-time dimensions, you will find similar plots. So this motivates us that whether we can just have some analytical understanding at this infinite limit. And so originally what we did is something kind of awkward or something pretty fun, that actually we reconstruct these 4-point cohesion functions using the numerical data. So, and at the end of the day, we get this rather complicated looking 4-point cohesion functions, and that's somehow magically reconstructed from numerics. And later, after talking to colleagues, we realized that there's a simple way to view this 4-point cohesion functions. That is, you can consider it as subtraction of a free theory and a generalized a free fermion theory and a generalized free theory look like this. So this free fermion theory is slightly different from what we usually think about. So this free fermion theory is that consists 2 parts. One part is an O(n) Majorana fermion. Let's say let's stay in 3D. And this eta is an O(1) Majorana fermion. So then you can write down a fermion bilinear, this psi bar eta, which will then be an O(n) vector, which is a bosonic operator. And then you can calculate its 4-point cohesion functions and show that this subtraction exactly equals to this infinite N 4-point cohesion functions constructed from numerics. And this actually tell us a mechanism for the appearance of bootstrap kink. So the idea is following. So let's say we have 2 4-point cohesion functions or 2 theories, and then in this case it's a free fermion theory and a generalized free theory. And what you can see is that the generalized free theory spectrum is actually a subset of the free fermion spectrum. So then it's legal for you to subtract 2 4-point cohesion functions, as long as the subtraction of the squared OPE is non-negative for all the operators in the generalized free theory. And then this 4-point cohesion functions will always be crossing symmetric and consistent with unitarity. And you can do one step further. That is, you can just so if you look at those 2 theories, the leading operators in the O(n) rank 2 tensor have scaling dimension 2d minus 2. However, you can, by choosing the prefactor in a proper way, and you can making this leading operator to be canceled during this subtraction by keeping these relations, and then these operators will disappear, making the leading operators to have scaling dimension 2d. That's actually explains that why here at this d-1, you see a jump that from the scaling dimension to 2D minus 2 to 2D. And this jump is nothing but that you subtract 2 4-point cohesion functions. And this mechanism, of course, is not that easy to satisfy in a general case, because first you need is like 2 theories whose spectrum are very similar. In higher dimensions, we only know 3 theories have this properties. Some interaction theories may have, but we just don't know such examples. At least I don't know such examples. So that may suggest that even though in the infinite limit, we can understand this 4-point cohesion function through this subtraction, maybe for finite n, it doesn't really have this structure. In particular, for SO4, for SU to level 1 Western Witten, we know it's not this structure. So maybe in the infinite n, it's just a coincidence. One thing you might think is that at finite n, that since you get some free fermion piece, then at finite n, maybe the theory contains some CFTs perturbing from the free theory. However, if you want to use that scenario, then you have to deal with this subtracted piece. That's some perturbed or interacting type of generalized free theory, which at least making this kink hard to simply connect it to the non-CFTs like Gross-Naveau or QED3 that can be viewed as perturbing from the free fermion theory. Okay, so
Yin-Chen, sorry, I have a question. It's a stupid question. So I didn't get, what is the external operator combination of these two that gives rise effectively to this subtraction of 2? I mean, I didn't get this point. So this is, your conformal block decomposition is compatible with the subtraction of 2 4-point function.
Yeah.
But what is the, say, external primary operator such that you get this?
We don't know. We don't know.
Okay.
Yeah. So that's why it's hard to really understand what is happening for finite. What I said is just that this 4-point cohesion functions can be viewed as subtraction of 2 4-point cohesion functions.
No, but also you can just consider an operator which is the difference of phi I bar eta and psi I bar eta and phi I. And then if you expand all the brackets, then everything will cancel and we will just be left with these 2 terms, I guess.
But you get a plus and then you get also mixed
you get
terms.
Plus.
No?
You get plus, right?
Okay.
You get 4 i's times together.
Yeah, you're right.
And probably there's still cross terms, I guess.
Yeah.
And there are cross terms.
It's hard to really write down a simple 4-point cohesion function. What I'm trying to say is, it's just a way to view this 4-point cohesion function, maybe, but it may be not the right way to understand its physics, some of its physics. Yeah. Or it can be artifact. Yeah, I don't know. Okay. One thing I want to say is that this infinite n solution actually contains the full tower of higher spin conserved current. And it actually has 2 towers simply coming from this psi fermion and eta fermion. And so you can ask what can make it to be a good CFT at finite n. One hope is that maybe the second energy stress tensor, energy momentum tensor gets slightly broken, but we don't know numerically or theoretically whether this is the case.
Sorry, can I question about having 2 stress tensors? I'm a bit confused because I have a 4-point function.
Yeah.
Like what you can get is just the 4-point function. This difference and like this formula that you write is just your interpretation. So what you compute is a 4-point function. It has an expansion to conformal blocks. And how do you see from this expansion of conformal blocks that there are 2 stress tensors?
Yeah, from the conformal block, we cannot say that.
But then how do, I'm not sure, then I'm just not sure that this statement makes any sense because as you say, it's not clear whether you can actually interpret this formula as a correlation function in any particular
I think
theory. So I'm not sure how to interpret your statement that there are 2 stress.
Yeah, that's a good point. So let me first make a quick comment. The reason that from 4-point correlation function, we don't see this sector is because we are at infinite and limit. So then this piece is just gone, right? It's literally 0. And theoretically, we know that if we have a free theory, we have a theory with a full tower of highest spin conserved current. It has to be free, according to some work by Huang Madasena. And then, and also the center charge should be order of n, not order of 1. But if you just look at the 4-point correlation functions, it's not consistent with this either. The center charge is of order 1. So then that's motivates us that, yeah, that should be the right structure. If you just look at, let's say, infinite n free boson, you will actually, just from 4-point correlation function, you cannot say this piece, right? Because it's again just literally goes to 0 at n equals to infinite. So this structure, so yeah, directly from 4-point correlation functions, we cannot say this part, but I think there are several good reasons to believe this part also exists. So does this answer your question?
Okay, thank you, yes.
We are saying there is a weird feature about this 4-point function. Even though it's at infinite n, it looks like the center charge is order 1. And so this paradox.
If you literally take that 4-point correlation function. Yeah. But as said, if you just play with free boson at infinite n, yeah, so literally you don't say the 4-point function doesn't give you the energy momentum tensor, right? Okay, so at last, let me just quickly, let me just say that I think at this moment it's unclear about the nature of this non-Wilson-Fisher kinks. There are several challenges, like the operator contents doesn't fit any known CFTs in 2D. ON doesn't factorize except for O4, so then it's hard to make connections to a known CFTs. And there are, of course, many possibilities. One possibility is that maybe just an artifact, except for special N's and D's. Even this is true, then it still detects this SU to level 1 and tells us something about these SO5 deconfined factorizations. It solves some problem that we care about. And another possibility is that it could be some non-local CFT without any energy momentum tensor. I mean, for general N and D's. For example, it could be boundary CFT or some conformal defect.
Sorry, but
and
can you not see the stress tensor in your correlator? Can you check the coefficient? I'm confused.
Numerically, we didn't try. I think in principle, yes, but so far we haven't tried it yet. In the infinite unlimited, it has this energy stress tensor, but it could be broken at finder. Yeah, we don't know. Yeah, but I think we are working on it. And also there are some interesting proposal that maybe you can look at some other symmetries, for example, SUN, then you get some QED3 theories. So I think this proposal is quite appealing, but there's some work need to be done to really, in order to reach a conclusion. And indeed, we find some, I have some quite a nice plot which are clearly are not in favor of this scenario. If you are interested, I can talk about it during the question session or maybe after the talk. And the last possibility is that it could be a new family of local CFTs that were not known before. But all those possibilities so far, for most of them, we don't know which one is more likely. And I think it requires more precise numerical data on one hand. So for example, it may be done with mixed correlator Bootstrap, and we are currently working on it. And I just want to quickly wrap up. First of all, I hope that I give you some sense that this non-Wilson-Fisher CFTs are relevant to certain condensed matter theory or even materials. And we discuss a family of Bootstrap kinks, which we call non-Wilson-Fisher kinks. And some of those non-Wilson-Fisher kinks are relevant to the safeties we are interested in condensed matter. In particular, we find this SU2 level 1 version of Witten model, and we find its dimensional continuation suggests that the phase transition is SO5, deconfined phase transition is pseudo-critical. And at the infinite end, we get exact solution, which hints a possible new family of safeties. Okay, so thanks, and please stay safe.
Thank you very much. Any other questions?
Yes, I have a question, Yin-Chen. So I didn't get the point. So when you study the O4 plus epsilon in 2 plus epsilon dimensions, and then you show that up to 2.7, you expect some annihilation fixed point. So shouldn't we expect to see 2 kinks that, so the other CFT, is it obvious that it doesn't lie at the boundary and gives you another kink? So why don't you see 2 kinks before the annihilation?
Yeah, that's a good question. So I think first of all, there's no a priori that every CFT should sit at a kink or even saturated numerical bound, right?
That's true, so, but then the annihilation can also happen in the middle if you wish.
Yeah, what I believe is that in this case, the other kink should stay in the bulk of the CFT, not at the boundary. The reason is because for that CFT, you get a relevant singlet, right? So then you cannot really find it. On the numerical bound, the singlet is always irrelevant, even at 2D.
Yes.
So that means there's no way that that CFT will saturate the bound that allows taking at a kink. So I believe it's someplace deep in the bulk. Yeah. There may be some way to find it, but not from the single correlator.
Maybe with some extra assumption.
Yeah, you could try to, for example, impose that it's just one relevant singlet below.
Yeah.
And
Yeah. We can always impose some assumptions, but what I found in reality, in many times, those assumptions just don't give you anything new. It doesn't change the plot at all. That's a sad reality, what I encountered a lot.
Yeah, that's true. Okay, thanks.
One more question. You mentioned at some point a large K expansion in your nonlinear sigma models.
Yeah.
Is it really possible to do a large K expansion or directly in 3D?
Oh, no. I don't think so. What they start is 2D. And then,
and of course I know how to do that, but is it possible to do it in generic D?
I don't know. People tried very complicated things like, I think Chen Ke Xu has tried like double or triple expansions, like dimension, some non-local thing, and K, something like that. It's rather complicated. But I guess the short answer is that it's unclear how to do it in 3D or generic.
H theory description, I know how to do it. But in terms of the sigma model, it seems difficult.
Yeah. You know, the sigma model is non-renormalizable beyond 2D, right? That also makes it hard to really do perturbation calculations. That's my understanding.
Oh, of course, yeah.
To me, that's more like intuitive Lagrangian that can give us some idea about the physics is happening there. But quantitatively, it's hard to make anything out of it. Maybe Bootstrap can, so that's, yeah.
And what do you know about K equals 1?
I think from these results, it suggests that it's pseudo-critical or it's complex at 3D.
What is the difference between pseudo-critical and complex?
They're same, they're just different names. Sorry.
What's the difference between complex and first order?
Yeah, so I think in general, if the complex fixed point is far away from the real plane, then you will say strong first order behavior. If it is close to a real plane, then you will say the so-called weakly first order phase transitions, or we call it pseudo-critical. I guess then this answers your question. So complex CFT probably refers to a general behavior that the CFT that can happens in a complex parameter space. But by pseudo-critical, we usually means that this complex fixed point is pretty close to a real plane such that you will see some approximate conformality, conformal behaviors even in a real Hamiltonian.
Yeah, maybe for some range of length scales.
Yeah.
Okay, thanks.
Any other questions?
Well, if there is time, I would like to see those comments about possibility of other symmetries that relates to the work of Jin and David.
Okay, maybe let me just use 1 or 2 minutes to try to say whether I can make any sense of it. So I guess the idea is that that they show that different symmetries may yield the same bound. That's really a nice observation. In particular, for example, in this Jin's paper, earlier paper, he proposed that in 3D, maybe you should look at SU and adjoint, and then if you try to bound singlet, you will see a kink, same as this ON kink with some identifications of this N and F. Then this kink may correspond to a QD3, that's his proposal. So, if this proposal is correct, then there's some very simple and sharp predictions. For example, you can easily tell that whether the theory should be an ON theory or a QD theory, QD3 theory, by looking at certain operators. If it's intrinsically ON theory, then you should expect that this antisymmetric tensor will be branched down to two wrap with odd spin like this. Then since in ON theory it's conserved, so then you will easily claim that the operators in those two channels, the spin 1 operator in those two channels will be conserved in 3D, let's say dimension 2. But in QD3 theory, the scaling dimensions in this channel are actually quite different. In large N, it's 5 + 1 over NF corrections. You see they are quite different, then you can just use this to detect which one is true. So, okay, this is some plot. So here is like a plot for SU4, there's a plot for SU20. So if you don't impose any gap in this channel, that's just except for unitary bound, you say a kink, and Jin claimed that it corresponds to QD3. But now what you can do is that let's just impose a tiny gap, let's say 0.2. You see, its larger value is 5, and it's SU20. So you should expect this gap is super safe. Then you say the kink justifies. So I think that's is a very clear and strong evidence that this kink is not QD3. And it also suggests that the intrinsic symmetry, at least in 3D, should be ON rather than SUN, because
can I say something?
Tiny gap in this channel already kills the kink.
Can I say something?
Yeah.
Okay, so I think you misunderstanding my claim. So I'm not saying that this kink provide a SUN adjoint symmetric solution to the coordinate equation and gives us exactly the QD3 fixed point. That's not my claim. My claim is that actually I already showed the strong linear invariance in my results that the solution to the coordinate equation and this kink has exactly SON symmetry. It's not SU and adjoint symmetry. And my claim is that this SON coordinate symmetric solution comes from symmetry enhancement of the IR fixed point of QD3. That's my claim.
Yeah.
So what you said here is totally misunderstand my claim.
Yeah.
I'm not saying
I'm not.
Yeah.
Sorry, I'm not.
Sorry.
Yeah.
I think, Jing, because I was there in yesterday's talk, that construction you have does not change S-channel spectrum, right?
Yes.
But here, I mean, we already showed the large N S-channel spectrum. It has some weird behaviors, like order 1 central charge, and also it contains higher spin spectrum, which doesn't decouple at infinite N. So I think it's already pretty clear it's not QED.
No. I mean, because there's a symmetry enhancement, and also besides that, this is a general problem. If you go to singlet band, the band is very high, right? And this it convex very slow. So I'm not saying this can exactly correspond to the concrete. So my guess is that because here we believe that this can include both the numerical effect and also physical stuff. And my claim is that this physical content comes from the fixed point of QED3. That's my conjecture. But I'm not claiming that there's no numerical effect mixed in this solution. And also, because previously Yin-Chen, his claim is just based on the symmetry. He claimed that this Carson equation of this is SON symmetric, so it cannot be QED3. But that's totally misunderstand my claim. I know I showed it clearly that the Carson solution is exactly SON symmetric. But my claim is that this SON symmetric solution comes from the QED3 solution, fixed point.
While you're arguing, can I see the previous slide, please?
This one?
No, I have no question. I just wanted to see the slides.
Okay.
So, sorry, I have a question. Like you're just saying, from what I understand, you're saying that the plots from yesterday, the kinks don't represent QED free, but that doesn't necessarily mean that, you know, even in this case that you expect to have SO5 symmetry, there's no other fixed point with the symmetries that QED free actually has, right? It's just more in the allowed region than what you've already shown, right?
Yeah, QED
okay, so you're not implying that QED free does not have QED free does not have a fixed point somewhere in the allowed region, right? Or you're not necessarily implying even that it necessarily for NF equal to that necessarily it has an SO5 symmetry and it's a complex CFT, right? It could be that there's the possibility that there's another fixed point with the genuine symmetry that exists in the UV.
That's true, yeah. I guess all I want to say here is that this kink doesn't correspond to QED3. It could be some mixture between QED3 and other things, that could be, but at least I guess the fair claim is that I guess also that's probably also what Zhijing want to make during what he said, that this kink itself doesn't correspond to QED3.
No, okay. I want to can I claim my restate my claim again?
So okay. Sorry guys, I feel that the discussion is very interesting for a few experts, but probably not for everybody. So I suggest that we end the talk here, and I will, of course, I don't want to interrupt the discussion. So I made Yin-Chen the host, and the subgroup of people who's interested in this debate, which obviously should be sorted out, since there seems to be a disagreement, are of course welcome to stay and continue discussing. So thank you very much.
That's a wonderful idea, yeah.
Thank you.
Yeah, thanks.
So you are the host now.
We should thank Yin-Chen once again for his great talk. It was very, very
great talk. Yes.
Thanks.
So you are Yin-Chen. You are the host now. So I have to go, but whoever wants to stay and hang out, you can discuss with them.
Yeah. So does it mean that I can? Yeah. Thanks.
Means that you are in charge, and that the Zoom channel remains open for whoever wants to keep discussing.
Yeah.
Thank you.
Yeah, thanks.